Hi, welcome to this video on propositional logic. In a bit, you will learn more about the role of logic within the fields of mathematics and computer science, the place of propositional logic within the field of logic itself, and of course what propositional logic entails. So what is logic? The rules of logic give precise meaning to mathematical statements. This is in contrast to natural language, such as English, which can be ambiguous. For example, consider the following statement. Everyone loves someone. Now this could imply that every person loves a possibly unique or more than one other person. However, it could also imply that there is a single person that is loved by everyone. By defining the statement using logic, one could avoid such an ambiguity. These rules of logic can also be used to distinguish between valid and invalid mathematical statements. As a consequence, it also allows us to reason about what makes up a correct mathematical argument, that is, a proof. As a result, logic can be considered at the basis of all mathematical reasoning. Now, as you might know, mathematics is not a purely theoretical field. It has many applications, including computer science. Within computer science, logic can, for example, be used to verify the correctness of algorithms, so whether an algorithm always produces a correct result. Furthermore, logic plays an important role in symbolic artificial intelligence and is also used in the design of programming languages. Then propositional logic specifically. Propositional logic is an area within the field of formal logic that deals with propositions. It is a rather simple logic that allows us to express the relation between propositions and infer knowledge from these relations. So, what exactly is a proposition then? Well, luckily I've got an entire slide just on propositions. So, a proposition is a declarative sentence, that is, a statement that declares a fact that is either true or false, but not both. Okay, all good so far, so let's look at some examples. So, say 1 plus 1 is equal to 2. So, is this a proposition? Well, it declares a fact, and in this case the fact is true. So, yes, according to the definition, this is a proposition. Now, what about the statement 1 plus 2 is equal to 4? Is this a proposition? Again, it declares a fact. However, in this case, the fact is false. But according to the definition of a proposition, that does not matter. Simply the fact that it declares a fact that is either true or false makes this a proposition. So yes, even though the fact is valid, it is still a proposition. Now what about the statement in natural language? For example, Amsterdam is the capital of the Netherlands. And I'm abbreviating Amsterdam and Netherlands here. So again, it says a fact. In this case, a fact is true. But again, because it says a fact, yes, this is a proposition. Then what about asking ourselves what time it is, which I'm abbreviating as what time? Well, no, this is not a proposition because it doesn't declare a fact. Then finally, we have a mathematical statement x is equal to 4. Is this a proposition? Well, it might surprise you, but no, this is not a proposition. Why? Well, we have not assigned x any value, so it doesn't declare a fact. We don't know whether this is true or false. Were we, however, to, for example, say, well, we assign the value 3 to x, and then combine this into the statement 3 is equal to 4 by substituting x with 3, then yes, now it is a proposition because it states a fact that in this case is false, obviously. So by assigning a value to x, we can make it a proposition. Okay, so now that we know what propositions are, what else does propositional logic consist of? So remember how we wanted to avoid ambiguity through logic. This is one of the reasons why we want to have precise rules on how to express ourselves. These precise rules are what is referred to as syntax. Syntax refers to a set of rules that determines how we are allowed to express statements. In propositional logic, syntax comprises two parts. Propositional variables, which are variables that represent propositions by convention using lowercase letters, often P, Q, R, S, and then just following onward in the alphabet. And logical connectives, which are operators that allow us to express relations between propositional variables. So the way to think about propositional variables is simply that we have a name, for example P, that stands for a certain declarative sentence. And logical connectives have a good analogy with regular mathematics. For example, you might be familiar with the formula y is equal to x. In this case, you know y and x are variables. These could have just as well been propositional variables. And the equality sign is called an operator. And it operates or works on two values, two sort of inputs. Therefore, we say it has an arity of 2. Within the context of this operator, we refer to y and x as its operands. Hopefully that clears up any doubts you might have had about the terminology. So now that we have seen propositional variables, let's look at those connectives that make up the syntax of propositional logic. We will consider 7 connectives, 4 so-called base connectives, and 3 so-called derived connectives. Derived connectives are connectives that can be defined in terms of another connective. And that's what we see also in the definition, that these derived connectives use definitions that we have seen before. So let's go over these base connectives first. So the first column is the symbol of the connective. The second column is the name of the connective that we use when we are referring to it outside of a propositional formula, so just on its own. The pronunciation is how we define or how we name the connective in a formula. So for example, for the conjunction connective, we say phi and psi instead of phi conjunction psi. And phi and psi stand for arbitrary propositional variables. For example, this could have just as well been phi and q. So let's go through these together. So absurdity, denoted by an upside down T, is pronounced as bottom in a propositional formula. And the intuitive meaning is that it never holds. And what this means, you will see in a bit more detail later on. Then we have the conjunction, and we pronounce it as step before us and in a propositional formula. So we, for example, have P and Q. And this relation holds if both P and Q individually hold. Then we have the disjunction, which we pronounce as, for example, P or Q. And this relation holds if either P or Q hold or both hold. Then finally we have implication, which we can write using, again, the symbol of the connective P implies Q. And this means that if P holds, then Q also holds. And again, we will see examples of these connectives. So what about derived connectives? So again, they are defined using the connectives we've seen so far. And so their meaning follows from this definition. So we have negation, which we pronounce as not phi, which is, for example, not P. And its definition, it comes down to how we flip whether it holds or not. So say P didn't hold before, then negating it, now it holds. If it's held before, negating it, now it does not hold. So it sort of flips that around. And it will be really clear when we look at the truth connective now. So we call top, that's simply that symbol. It has an arity of 0. That's also what you see in the pronunciation. It just is used on its own. It doesn't involve a phi or psi. It has no operands. And its definition is the negation of bottom. So while bottom never holds, because we flip it using the negation, top always holds. Then finally, we are looking at the by implication, and we pronounce it as phi if and only if psi. So that abbreviation stands for if and only if. So what does that mean? Well, it's really clear from its definition and also from its pronunciation. So if and only if, phi if and only if psi. So if phi holds, then psi holds. That's the first if, that's this part. And we know that and is the name for the conjunction, so that's why we see a conjunction here. And only if. So what that means is phi if and only if psi. So if psi is true, then it must be the case that phi is true because of this only specifier. That's exactly what we see here. If psi is true, then phi is true. And because the implication goes from phi to psi, also from psi back to phi, we call it by implication because we're working with two implications. So now that we know what the connectives are, we can actually start forming propositional formulas. So before doing so, we look at two definitions. An atomic proposition consists of a single propositional variable. So we would refer to an atomic proposition, for example, P, Q, R. These are atomic propositions. Then we also have compound propositions, which are formed from existing propositions using logical connectives. Now, what do we consider under existing propositions? For example, the atomic propositions, so P, Q, and R. Then we use logical connectives to form new compound propositions. So let's look at an example from above. So remember conjunction. It works on two values, phi and psi, or in this case as an example, P and Q. So let's actually, because we know P and Q are existing propositions, let's actually use those two and create a new compound proposition using conjunction. So we take conjunction and it needs two operands, one at the left side, one at the right side, so P and Q. So now this is now a new proposition, a compound proposition, that now also belongs to the set of existing propositions. Now say I want to apply conjunction again, then I could, for example, take P again, use the conjunction, and now at the right hand side I could also just as well take this compound proposition, so P and Q, that we defined previously. And through this manner, we can create propositional formulas. So let's look at two examples. So remember that propositions are declarative sentences. They are statements of facts. So Socrates has no umbrella. Yeah, that's a proposition. He does not get wet. Yeah, that's also a fact. It's a proposition. And now notice how we combine both propositions using and, which is a connective we have seen before. It's conjunction. So how do we go from propositions to propositional variables? Well, just a matter of design and matter of taste, basically. So Socrates has no umbrella. Let's say I want to represent that using U, the propositional variable U. He does not get wet. Again, it's a choice. I could simply say this is W. However, what I would prefer in this case, but again, it's preference, it's a matter of taste, is I would like W to refer to getting wet, or he getting wet, and then apply negation to represent the does not part. So we get this. We could have just as well said, however, that W stands for not getting wet, and if you would then like to model getting wet, we would instead have a negation there instead then. So let's write it down a little bit clearer. So U and not W. Let's look at the second example. So if it rains and Socrates has no umbrella, then he gets wet. So we have an if then, that's an implication. So if the left hand side, then the right hand side. So the right hand side we already know, because I defined getting wet as W, so he gets wet is simply W. Right? Remember, because does not get wet was the negation of W, so getting wet is W. Then on the left hand side we see it rains, that's a statement, that's a proposition, and that's a connective we already have seen before, now multiple times, conjunction, and Socrates has no umbrella. That's one I've defined above already using U, so we can reuse that here. If it rains, let's just create a new propositional variable, for example, R. So writing it down fully, we will get R and U implies W. And just to be sure that the meaning comes across correctly, because if the complete left hand side is true, then he gets wet, let's use parentheses. Okay, so now you might wonder, okay, did we actually need parentheses? Was that necessary? Well, consider the following example. One might form the formula P and Q implies S. Now, is this logically equivalent to what we saw before? So P and Q implies S. Or is it logically equivalent to P and Q implies S? So the first case. Well, we actually don't know. It's ambiguous based on the definition we've seen so far. However, there is a solution in this case. Just like PEMDAS defines the order of operations in mathematics, we can also define an order for propositional logic, and we do so using two properties, so-called precedence and associativity. Precedence says something about the order of operations to apply. So just like we needed to do multiplication before addition, this simply says first do negation, then do disjunction and conjunction, and then do implication and by implication. So these form sort of groups, sort of levels. So negation is the strongest, then we have the level with disjunction and conjunction, then we have the level with implication and by implication. So let's look at an example again. So P and Q implies S, like we saw above. So now the question is, did we actually need to use parentheses if we use the precedence and associativity rules like defined here? So we see conjunction, and it has a stronger grouping or higher precedence than implication, so we need to perform it first. Remember that conjunction takes two operands, one at the left-hand side and one at the right-hand side. So in this case, it is defined as if there were parentheses around the conjunction. And then after doing that, we would, again following the precedence rules, we would actually perform the implication. So looking back at the example we saw above, no, parentheses were actually not necessary here. The meaning would have been that parentheses were there using the precedence and associativity rules. Now we can also look at another example. For example, P and Q and S. Now the question is, how do the parentheses work here? Because we could do P and Q first, but you could also do Q and S first. However, which one is the correct one, right? We don't want ambiguity. Now notice that the precedence is the same for all operators, so we cannot use that to determine the order of operations. In this case, we look at associativity. So all operators are right associative, means that if we have the same operator, we try to group as most on the right-hand side. So for example, we encounter the conjunction, this conjunction first when going from left to right, and we want groups as large as possible at the right-hand side. So we open the parentheses here and close the parentheses here. That's basically what right associativity means. We could also look at this with three conjunctions. So for example, P and Q and R and S. And in this case again, right associative, we start grouping here, the largest one, and then for this inner part, we again want the largest possible group to the right-hand side, so we group one more time there as well. Now let's look at one final example. What if we have mixed operators of the same precedence level? So for example, P and Q or S. So in this case, this is undefined or is still ambiguous because precedence doesn't help us here. Associativity doesn't help us here unless we specifically define how this would work among operators of the same level. However, this often leads to more confusion than that it's really worth it. Because why would, for example, AND group stronger than or group differently in terms of associativity, right? So in these sort of examples where precedence level is the same among operators and there's no clear indication of which one goes first, we need to make it unambiguous ourselves by manually adding parentheses. So for example, if I want the conjunction to go first, I will manually group it like that. Okay, cool. So now that we are also completely clear about the syntax of propositional logic, let's look at the semantics. The video on the syntax of propositional logic turned out longer than expected. As a result, the semantics of propositional logic are covered in a separate video. Be sure to check it out. Nonetheless, thank you for watching the video until the end, and I hope you learned something new today.